Welcome. Thank you for coming. For this session, I will talk about the new full text search feature in Apache Cassandra. So let me introduce myself. My name is Duy Hai Doan. I am working as an Apache Cassandra evangelist for data stacks. Who is familiar with Apache Cassandra here? Please raise your hand. Okay. Don't worry, because I have a very quick introduction to Cassandra if you don't know. So let's start. This is the agenda. I will introduce very quickly Cassandra, and then I will explain the new full text search feature. Okay, and we will finish by some benchmark and takeaway. So this is a Cassandra cluster, right? So Apache Cassandra is a distributed NoSQL database. Here I have a cluster of 8 machines. And what you should know is every time you insert data into Cassandra, you need to provide what we call a partition key. So what is a partition key? A partition key is like a primary key. You have a table, you have a primary key. So in Cassandra, the partition key is very similar to a primary key, right? And when you insert data with a partition key, Cassandra will apply a hash function to this partition key. You get a numeric value, which is a token. And of course, the range of all possible values for token is very large. So the idea is, okay, if I have a cluster of 8 machines, Cassandra will split my token range into 8 equal intervals, right? So now if I insert the data and the hash value is inside this interval, Cassandra will distribute the data on this machine. It is how it works. And of course, we choose the hash function to be very distributive so that you don't have hotspot, and it guarantees a uniform distribution on all the cluster. In Cassandra, we have all the tables are distributed. What does it mean? Suppose you have a user table, right? User ID, which is the partition key. So this is one partition. A partition is a physical row on disk. So you have user ID, which is partition key, first name, last name, age, and so on. And thanks to the hash function, each partition will be stored on different machines. Right? Coordinator node. Every time you query data from Cassandra, insert, update, delete, select, your client will contact a node which is called a coordinator. So what is a coordinator? It is not a master, because Cassandra is masterless. There is no master. A coordinator is just a machine which receives the request and is responsible for this request and only this request. And because each machine in the cluster knows about the topology, knows about the token range, the coordinator will compute the hash function based on the partition key you are giving. And it knows that it needs to distribute the data here and here and here, because we replicate data 3 times, replication factor 3. So it will distribute the data to 3 copies. If I am unlucky and this machine is down, I don't care, because anyone in the cluster can be a coordinator. So the architecture is symmetric, right? And that's all for introduction. Very, really simple. No question? Okay. Now let's talk about the full text search feature, SASI. It's called SASI. So what is SASI? SASI is SS table attached secondary index. So before, we have a native secondary index implementation in Cassandra, but it is not very fast and not very performant. This is a new implementation. And the idea of this implementation is the index file will follow the same life cycle as the data files. Who implemented this new index? Well, a bunch of people, they are working for the same big company, you can see. Those are their GitHub account, so public data. So those 5 guys, they have developed SASI internally, and they have contributed to the open source project. Why is it better than the original native secondary index? Because you have new data structure to index data. Now you can use range query, like greater than, lower than, and so on. And we have also full text search options. So let's see some demo. I have a table in Cassandra, which is album, okay? It contains, let's see how many. So don't do that in production, right? Counstar, it will do a full cluster scan if you do that in production. It's very bad. So just for the demo, because I have a single machine, so I have 112,000 albums, right, in my cluster. Select star from music album, limit 10. Let's see some example. Okay, here are my data. So you have the artist name, the country, the ID of the album, the title, and so on. Okay, now I want to be able to search data on my album. So let's create some index. I want to be able to full text search on the title, right? So I create a custom secondary index on the title with contains mode, which means that I will be able to search substring. I define a standard analyzer with stemming, local, skip, stop, word, okay, all those options for full text search. I want to be able to search on the artist name, mode contains, but this time I am using the non-tokenizing analyzer. It means that I will not split the artist name into different tokens because I don't need to. I want to be able to search on country, mode prefix. It means that I can only search by prefix and not suffix. And also to be able to search using the year, the release year of each album. Okay. Now let's see some example. We are in Serbia, right? Give me all the albums which contains, which is chai, right, in Serbian. Deka. Okay. Right. You can, because we have full text search, we can say, okay, give me all the album whose title contains DE. This is the contains syntax. DK, deveti, de facto. Okay. Give me all the title which finish by, sorry, NA. So suffix search. Okay. So don't blame me for my choice of music. It's not my data set. I just get it from the internet, right? Okay. Fine. Now let's change country because I have only 10 examples for music from Serbia, but I have a lot more music from USA because the data set have more music from USA. So let's say give me all the albums released in USA that contains love. Contains. Okay, love, love, love. Let me find you something interesting. Where is it? Glovers. You see here? What happened? Glovers. So because I said contains love, so Glover is also a correct result, right? And now let's say, give me loving. It also returns all the title which contain love. Why? Because full text search, because of stemming. Loving and love is the same word in English, right? So you put loving, it returns you love. Another example. Loving and feel. Love, feeling. Same word, full text search. Okay. Let's move on. And oh yeah, I just forget, you can mix many predicates, right? You can search on country, on the years, and well, if I put here 2010, I will have maybe less result or maybe no result. Yeah, because I restrict the year. So how does it work? First, on the cluster. As I said, the data, remember the 5 minutes introduction, the data are distributed all over the cluster. It's the same for the index. It means that in this example, I have a secondary index on the user country, right? The index are local. So on this machine, I have some user which are living in United Kingdom. So the index will point to those users. But in another machine, I have some other user which are also living in the United Kingdom. So I have also index for those people. So the index data are also distributed. It has a consequence. When you send a request using secondary index for Cassandra, the coordinator will first issue a query on some machines with the concurrency factor. First round of query, give me the result. You get some result back. Imagine that you say limit 1000 and you don't have enough result. Well, the coordinator will send another round of requests by increasing the concurrency factor, giving more result. Still not enough. Give him more result, and every time it will increase the concurrency factor, right? This is how it works. So this is the exact formula of how to compute the concurrency factor. So it's complex, and it is based on the assumption that we assume that the data are distributed uniformly on a cluster. So if you can get some statistics about how many rows you have on one machine, you can estimate that on the other machines you have the same amount of rows. Right? You can have more details about this formula on a blog post I wrote. I am not going to explain into the detail those formula, just to show you how it works. There are some issues with this kind of distributed index. If you issue a query with non-restrictive filters, well, eventually you will scan the whole cluster. If you have a cluster of 1000 machines, you will scan 1000 machines, which is bad. So the solution is always put a limit, right? If you have 2 billion of rows, probably you don't want to fetch 2 billion of rows. You may be interested in 100 results or 1000. So always put a limit. Second caveat. Imagine you have a one-to-one index. For example, you create index on user email. Let me ask you, how many users do you have per email address? 1 or 0? Not 2, not 3, right? Because email address is unique for each user. So imagine you query with, you are searching user by email. First query, not found. Second query, not found. Last query. At best, you will scan your whole cluster, and maximum you will find one user. This is the best case. The worst case is you scan the whole cluster and you find 0 user. Right. So for this kind of one-to-one index, it is recommended to use materialized view, which is a new feature in Cassandra. So you can create a materialized view, which is a duplicate of your base table, and you put the user email as primary key. And in this case, when you are looking for user by user email, because it is a search by primary key, it will be very fast. And because the user email is the partition key, you only contact one single machine and not the whole cluster. Last issue, imagine that you want to scan your whole cluster because you are doing some analytics, right? You want to compute some statistics on all of your users. Of course, in this case, it makes sense to fetch all the data out. It is not recommended to use this architecture. So you have a single client and then you are asking for all the data out. It is recommended to use a Spark, Apache Spark. Who knows Apache Spark here? Okay. So you install a Spark worker on each Cassandra node, and then you can have a local read. You have data locality, and each Spark worker will just read the data locally on each machine. It will be much faster. Let's dig into the read and write path. So this is how it works on the cluster. Now, how does it work on a single machine internally? Every time you insert data into Cassandra, the data go first to commit log to guarantee durability. Then we put data in memory. And after that, we acknowledge the client that the data is written. But at the same time, because you have an index, we create also an index mem table, which contains only the index data. Right? The data structure used by SASI is very simple. If you have prefix index mode, it will use concurrent radix tree from Guava. Contains mode, it will use concurrent suffix tree, which allow you to query data like this. And if you have a data type which is not text, numeric value or UUID or timestamp, it will use concurrent skip list set from JDK. Okay. We cannot keep data in memory forever. So after some time, we flush the data to disk. At the same time we flush the original data to disk, we are also creating the index data structure on disk at the same time, right? Because the index data is following the same life cycle as the original data. Same behavior for compaction. So compaction in Cassandra is sometimes there are too many data files, so Cassandra will merge them into a bigger one. The same for index file. All the index file will be merged into a new big one. So, summary. Index files are built on mem table flush from memory to disk or on compaction. To avoid out of memory issue, if your index data in memory is bigger than 1 GB, SASI will start flushing incrementally some segments of your index data on disk, and then we merge all the segments together. The consequence is, if you are using SASI, this new index, it will cost you, of course, bandwidth on CPU and disk, of course. There is no free lunch. Now, how can we use those index to reply to the query? Well, first, when you send a query with a where clause, it will be sent to the query planner, we will see later. And then SASI will load chunks of 4 kilobytes of index data into memory to perform search, primary search. And then, in fact, in the index file, we are only storing the partition key. We don't store the whole data. We just store the partition key so that we can go back to the original data file from Cassandra and read the actual data. So this is how it works. You have your user and the country, and if you have the index on the country, each index file will store the offset to each user in one partition. Right? We are going again into the detail, low-level detail. So this is the layout of the index structure. You have a header block, a data block, pointer blocks, and some metadata. Please notice that all those blocks have 4K. They are 4K multiple. Why 4K? Because the block size of modern disk are 4 kilobytes. So we align with the block size of disk. The header, well, it contains the min term, so the min value of the index. Imagine you have, I don't know, year as index. So you have the minimum year here, the maximum year here for this data file. So you can skip. It helps to skip. For example, give me all the data between 2010 and 2016. If the min and the max is, I don't know, 90s and 92, you can skip reading the whole index file. The same for the partition key. We keep the min value and the max value of the partition key, so we can skip reading those files very fast. Now let's zoom into the data block. Well, the data block, here we are storing the terms. So the terms are the index value, right? We have an offset array which point to each index value, and each index value will point to a token tree block which contains the offset of the partition key from the original file. So all the data blocks are here. Now we have a pointer block. What is a pointer block? You have a lot of data blocks, and we take the last value of each data block to put them into a pointer block. So this is the first level of the pointer block, and we repeat the same procedure. So on the upper level, we take the last value of the lower level, and so on until the root pointer block. So in fact, you have a tree structure, right? And this tree structure is used to perform search, binary search. So give me, I don't know, all the albums between 90s and 2010. So we will use all those blocks to search, binary search. We go down from pointer block to pointer block, and then we reach a data block. And when we reach a data block, again, we perform binary search. Is it less than term 100? Is it greater than term 15? And so on. Binary search. The query planner. This new index comes with advanced query planner. The idea of the query planner is to build a predicate tree and to push down all the predicates to optimize. For example, this is my query. Give me all the users where age less than 100, first name start with P, and first name different than PA, and age greater than 21. So this is the original predicate tree, right? You have N. First, because the N predicate is associative and commutative, we can merge those branches together, right? It gives you that branch. Okay. Not equaled. Not equals is an exclusion. So it will be transformed into an exclusion on a range scan. So here you have all first names start with P, but not PA. So it will be merged into the same predicate. Start with P, exclude PA. Last optimization, again, we have two N close here. With the age, we can merge them together into a range scan. some benchmark. So I had some a cluster of 13 bare metal machines, 6 CPU, 64 GB of RAM, and a lot of SSD. And I inserted a data set with 13 billions of rows, one numerical index with 36 distinct values, two text index with 7 distinct values, and one text index with only 3 distinct values. What does it mean? It means that you have only 3 distinct values for 30 billions of rows. So the index is very dense. Right? I want to stress test this new implementation of secondary index. Result. So I did a full table scan using a collocated Spark with no limit. It means that it will fetch all the data out of Cassandra on 30 machines, distributed. When I have one predicate, I fetch 36 millions of rows. It takes me 600 seconds. And the more I add predicates, of course, the more I filter. So the less I have rows, and of course the query time will decrease, except this case, right? I add one extra predicate, I have less row, but still the query time is a little bit bigger. Why? Because do not forget that when you are using secondary index, you need first to read the index file. And it is not free. It has some cost, right? And the more you read the index file, and the more it is expensive, right? So sometimes maybe it is more expensive to read the index file than the original file itself. This is a well-known issue with query optimizer. If you create an index and the index is not restrictive enough, you will fetch half of the data. So in this case, it is much less expensive to do a full scan than to use the index, in fact. Right? Another detail, very important detail, be careful with full text search and contains predicate. My original table album, I have 110,000 records. It took me 6.8 megabytes on disk. And I created an index on title contains. The index size is 41 megabytes, which is 6 times bigger than the original size. Why? Why is it? Because of the contains. What is contains? Contains is, imagine you have a big title. SASI will take all the substring of this big title. Right? So it is very, very expensive. Be careful with contains. Takeaway. People always ask me at the end, how does this SASI index compare to search engine, like Solar or Elasticsearch? Well, Cassandra is not a search engine. It is a database with full text search capabilities, but it is not a search engine. And it will always be slower. Why? Because we have 2 paths. First pass, we are reading index data on disk, and the second pass, we are reading the original data. If you are using a search engine, you only read the index directly, right? So it will always be faster. You don't have scoring on your full text search. You don't have order by, and you don't have group by. The ordering is random. The ordering, remember the cluster, the algorithm to search on the cluster. The order is the hash, the hash value ordering. So it is random order for you. So if you don't need ordering or group by, okay, you can use SASI. So the sweet spot of SASI is if you need multi-criteria search and you don't need ordering, grouping, scoring. If you mostly need 100 to 10,000 rows and you don't want to fetch out all of the data. You always know the partition key. If you provide the partition key instead of scanning the whole cluster, Cassandra will just scan one single machine because you provide a partition key. SASI is a poor choice if you have strong SLA on search latency, of course, because we cannot guarantee how long it will take, because we need to read the index data and then the original data. And if you need ordering on the search result, SASI is not for you. Any question? Yes.
Materialized view, is it distributed also?
No. Materialized view is, in fact, materialized view is, imagine you are creating manually another table and then you change the primary key so that the distribution of data, in my example, you put the user email as the partition key. So all the rows which contain the same user email will go to a single machine. That's the idea. Other question? No? Really? It's so clear that you don't have question? Come on, it's not possible. Thank you.